We've been learning about global climate patterns and how those global climate patterns affect the temperature and precipitation. In our next video, we will learn about biomes, which are regions of very specific temperature and precipitation trends. And we're going to learn the types of animals and plants that are found in those particular areas. But before we do that, we're going to talk about some other more localized effects that affect more localized processes or phenomenon that affect the localized seasonal temperatures and rainfall. So changes in the day length and precipitation are associated with seasonal changes. So you are probably all aware that our summer days are a little bit longer, our winter days are a little bit shorter. This has to do with the tilt of the earth. Didn't really cover that in the previous video, but I'm hoping that you are all a little bit familiar with that from previous science classes. And then, of course, our precipitation is also affected by the season that we will be in. So at the tropics along the equator, their rainfall is seasonal. They have 2 rainy seasons of equal length at the equator. What this essentially means is it's the rainy season all year round. But moving away from the equatorial regions, we start to see regional patterns in global variation of precipitation. So some of this is affected by the overall global patterns, and other are affected by regional seasons, regional topography, etc. So temperature can change, not just globally moving away from the equator, but also as we increase in elevation. So this is called adiabatic cooling, and this is cooling that takes place as we go up to higher elevations. So if you think of being at the bottom of the mountain and the top of the mountain is always colder than the bottom, no matter what season you're in. So the general trend is that elevation causes a 10 degrees Celsius drop for every 1,000 meters that you go up. So this is why our really high mountains are really, really cold at the top. So if you think about some of our famous large mountains like Mount Rainier in Washington or Mount Kilimanjaro, these are mountains that are snow-capped pretty much all year round, no matter how warm it is at the base. And this, of course, is going to affect the animals and the plants that live in this area. In chapter 44, we talked about species richness and how species richness changes as we move throughout a continent or throughout our larger regions within our continents. And we said that as you go higher, on a mountain ranges offer more opportunities for wildlife and species richness and diversity, because as you change in temperature, you get a variety of different plants that are adapted to those different temperatures and a variety of different habitats that allow those plants to survive and then support different types of animals. Another local effect on climate is a rain shadow. So a rain shadow sort of works like our tropical weather patterns at the equator, except that we have mountains that are forcing air to rise. So remember that warm air rises, and in contrast, cool air falls. And also that warm air holds moisture. So as moist air moves in from an ocean, so think about, say, the California coastline, because we're going to come back to California in just a minute. California coastline, we get moist air that moves in from the coastline, and it is going to move inland from the ocean, and all along the coast of California, we've got mountains. This doesn't work just for California, but that warm air is going to hit the mountains and it's going to start to rise. Remember that when warm air rises, it condenses into clouds And what happens when those clouds get too heavy? The rain falls back down. And so the warm air is forced higher against those mountains, so it just follows the pattern of the mountains up. It cools, condenses into rain, and rain falls back down on the front side or the ocean side of those mountains. Then on the back side, that air continues to move. The air, not the moisture, continues to move up and over. And so on the back side, we get air that sinks, but this air is dry. So our dry air is sinking, it warms as it falls because it's getting the elevation is getting lower, so it warms up as it falls. So at the base of those mountains, we have dry, warm air. And so the effect is on the backside of mountains, we often have what we call a rain shadow. This is a region where we don't have rain because the mountain blocks the rain from crossing over the tops of the mountains. And so we have this lush green area on the front side of the mountains, dry and warm on the back side. And then, sort of reiterating the problem, that warm air is going to rise, bring any moisture that it does have up into clouds. So here's a picture of Southern California. Southern California and the desert Southwest is dry for two different reasons. One is that Los Angeles is situated at approximately 34 degrees latitude, 34 degrees north. That falls right into that 30 to 60 degrees latitude where we have our driest regions. Remember, all of the water in the air has fallen at the equator, and that warm, dry air moves northward. And so that warm, dry air then falls over Southern California, most of California actually, and all of the desert Southwest. And then, so that is why the United States is generally a bit drier than our tropical regions. But the topography of California is really interesting because all along California, along the coastline and also inland, we have mountain ranges. And within California itself, we have this region in the center. This is the Central Valley. There's a lot of agriculture there, but it is very dry, and that is because of a rain shadow effect. So warm, moist air hits those coastal mountain ranges. The rain falls on the front side, and then that cool, dry air moves over the mountains to the Central Valley of California, which is relatively dry. Farther inland, though, we have the Sierra Nevada, which are very tall mountains, very high mountains, and it's a very long mountain range. Up farther north, we have several different mountain ranges in California, all of which act as a rain shadow for the rest of the Southwest. So everything behind that Sierra Nevada mountain range is essentially in a big rain shadow from those California mountains. But this is compounded by the fact that it is in the desert region of our global circulation patterns. So we get the rain shadow, and we also get that dry air between 30 and 60 degrees north. So you can see the outline on this map on the right. This is the Mojave Desert. This is a specific region within the desert Southwest. It is exceptionally hot and dry there. Death Valley, which is one of the hottest places on Earth, hottest and driest, is located within that Mojave Desert. A little bit more local to us in the Midwest is thunderstorms. So thunderstorms are a result of two different phenomena depending on the type of thunderstorm that we have. So the first is frontal thunderstorms. Frontal thunderstorms are essentially regional thunderstorms that are the result of warm, moist air coming up from the Gulf of Mexico or California, whatever you want to call it, warm, moist air coming up from the Gulf of Mexico, and then cool, dry air coming down from Canada. Now, these two patterns come together because of jet streams, which are air streams around the planet, circular air streams that follow specific patterns. We are not going to go into jet streams here, but just keep in mind that they do exist and that this is the driving force for these frontal thunderstorms. So what happens here is that the warm, moist air from the Gulf moves north and it collides with that cool or cold, dry air from Canada. And when that happens, that warm, moist air is going to condense and it's going to cool. And when it cools, when that air cools, the water vapor also cools and it falls as rain. So this is why we get thunderstorms in the summer on a regular basis. We get that warm air pushing up, cold air pushing down. They essentially crash in the middle. And the point where they collide into one another is called the front. So you may hear on the news or the local weather something about, we have a front pushing through. The front means the front edge of that cold, dry air or the warm, moist air. And where those two air patterns collide is where we get thunderstorms because of the cold air coming down, forcing the warm air to cool and condense. These frontal thunderstorms are the ones that give us severe weather. So tornadoes, lightning, hail, etc. And the difference in the cool, dry air and the warm, moist air, the greater the difference, the more severe weather you could potentially get. We also have a separate type of thunderstorms here called air mass thunderstorms. Air mass thunderstorms are much more localized. They're also known as pop-up thunderstorms. And this is where on warm, humid days, the ground heats up. Remember, when the air gets warm, or it's going to pick up moisture. So the ground heats up, it warms the air above it. That warm air picks up moisture. Remember that warm air rises. And as it rises, it cools. So we get our warm air rising. It's bringing moisture with it. As it gets higher and higher, it begins to cool. And then once it cools and all of the water in the clouds condense, it drops back down as rain. These guys are not interacting fronts and they're very localized. So these ones may create a lot of rain, but they tend not to be severe. Ocean currents and tides also affect local weather. We aren't going to spend too much time on this. I just want to point out that the rotation of the Earth, along with trade winds and jet streams, are also going to affect global and local weather patterns. So the Earth spins, it causes the air to spin, it causes the oceans to spin, and create these circulation patterns. So you can see we've got these circular patterns all around the Earth. And essentially the same thing happens as with the air masses. So as our water moves farther north, it's going to cool. And as it moves farther south, it warms. So closer to the equator, our water is going to be warm. As it cycles north, it becomes cooler. As it cycles south, it becomes warmer. Remember that the opposite happens in the southern hemisphere. So in the southern hemisphere, as the ocean currents move farther south, they become cooler towards the poles and then warm up as they move north towards the equator. Now, ocean currents are important because surface water drives wind patterns. Wind drives surface water patterns, and this affects local climate. It affects local weather systems. It affects the heat distribution around the planet, and it also cycles nutrients around. It moves nutrients around in the ocean currents, but it also does something called upwelling. So as warm ocean water is moved away, so for example, I know I drew over it and you can't see it too well, but as warm water is moved away from Australia, what it does is it allows cooler water to rise to the surface. This is called cold water upwelling. And cold water upwelling is really important for nutrient cycling. It brings nutrients from deep down, so it brings nutrients to the surface. So it brings up nutrients, which is important for aquatic organisms in those regions. Upwelling is going to be really important away from the equator. Around the equator, we actually don't have a lot of upwelling, and it just has to do with the way that the currents work on the equator. On the equator, the warm water is not moved away from any particular region, and so we don't get upwelling. We'll come back to that in just a little bit.